All right, let's jump right in. If you've been staring at that week 2 50-question challenge and feeling, well, maybe a little overwhelmed by the sheer volume of electrical concepts, you are in the exact right place. Today, in this explainer, we aren't just going to memorize answers. We're going to build a really deep working knowledge of the system. These concepts are essentially the master keys that will unlock the answers to that entire 50-question set.
So here's the thing about this foundational rule. It literally anchors everything you are ever going to do on a service call. Voltage pushes, current flows, resistance opposes, and a complete path allows electricity to do work. Whether you are dealing with a tiny residential thermostat or a massive commercial compressor, this basic relationship is the invisible force you're managing. Keep that in the back of your mind as we tackle these questions today. To get us through this, we're going to follow a technician's roadmap today. We'll hit AC power fundamentals, coils and transformers, motors and capacitors, essential meter testing, and finally, electrical safety rules. Let's get moving. Section 1. AC power fundamentals, the absolute pulse of our HVAC systems. Pulling straight from your review list, questions 3 and 14 asked us to identify the very lifeblood of our equipment. What power do most HVAC systems operate on, and what's the normal frequency in the US? It sounds like simple trivia, right? But honestly, knowing this dictates exactly how you set up your meter before you even touch a wire. And the answer is alternating currents, or AC, flowing at 60 cycles per second, which we call 60 hertz. The crucial point here is that unlike battery-powered DC, our systems rely on this AC power reversing direction 60 times a second. That alternating nature, that is exactly what allows us to step voltages up and down using transformers, which is a core requirement for HVAC systems. This actually brings up a huge divide out in the field. You'll see single-phase power, that's your standard 120 or 240 volts, mostly in residential setups. It's simple, it's everywhere. But you absolutely have to master three-phase power for large commercial jobs. Three-phase delivers a much smoother power with a lower line current for similar loads. That means smaller conductors and way more efficient motors. Moving right along to Section 2, coils and transformers. Let's look at how we actually control all that raw AC power. Think about this chain reaction for a second. Electric current enters a coil, right? That coil then becomes an electromagnet. And that invisible magnetic field physically pulls or moves a metal part. If you can visualize that basic magnetic induction, you'll instantly understand how contactors, relays, and solenoid valves operate. You're just using low-voltage electricity to create magnetism, which then does the heavy lifting of closing switches for high-voltage loads. Which brings us to question 1 from the Unit 34 section of your review. It tests your knowledge on how we safely route power to the thermostat. Obviously, we aren't going to run 240 volts through a customer's living room wall to a little plastic thermostat. So what is the standard control voltage? The exact answer you need is 24 volts AC. And a step-down transformer is the magic little component making that happen. It uses a high-voltage primary winding and a lower-voltage secondary winding. Thanks to magnetic induction, meaning there's no direct electrical connection between the two coils, it safely drops that incoming line voltage down for your controls. So if a thermostat is completely dead, checking for that 24 volts on the secondary side of this transformer is going to be your very first diagnostic step. All right, Section 3, motors and capacitors, the heavy lifters. Let's tackle question 2 from your week 2 list. We've got our controls safely set at 24 volts, but how do we give these heavy, resting motors the massive kick they need to actually start spinning? Because single-phase motors often just don't have the starting torque to get going on their own under a heavy load. So the answer to question 2 is that a capacitor causes a phase shift so the motor can start easier. It rapidly charges and discharges to create this shift. In a purely inductive motor circuit, current naturally lags voltage. But when we add a capacitor, we force the current to lead the voltage. This offset essentially creates a secondary, artificial phase, acting almost like a spark to provide that starting torque. If you've got a motor just humming but not starting, yeah, a failed capacitor is usually your prime suspect. Next up, Section 4, essential meter testing. Now that we know how everything operates, how do we actually prove the electrical path is intact? Question 15 asks us to identify our 3 best friends on a diagnostic service call. I mean, if you're going to verify a complaint and figure out why a system is completely down, you have to know exactly which settings to use on your multimeter. Your answers for question 15 are volts, current, and resistance, or ohms. But look, just knowing the words isn't enough. You absolutely must memorize these relationships to make sure your meter connection matches the live or dead state of the circuit.
Voltage is measured in parallel, usually with the power on. Current, or amps, you measure by clamping around a single conductor while the system is running. But resistance, this is critical. You measure ohms across an isolated component and the power must be absolutely 100% off, de-energized. Putting your meter in ohms on a live circuit is a really fast way to blow your meter fuses, or worse. And step by step, here is your rigorous meter check order. First, read the wiring diagram. It's your map. Second, use your eyes to inspect for obvious loose or burned parts. Then, verify your high line voltage, followed by the 24-volt control voltage. After that, track the voltage through your switches and contacts. Finally, measure the amperage under a working load. Never bypass a step, and seriously, never guess. Following this exact order is what separates the parts changers from the actual technicians. Which brings us to our final stop, Section 5, Electrical Safety Rules.
Look, all this diagnostic power means absolutely nothing if you don't go home safe at the end of the day. You've got to respect the hazards. Never perform energized work just because the scenario makes it sound like a routine thing. Shock paths and wet conditions drastically increase your danger out there. And remember, even a low voltage 24-volt line can spark, destroy a very expensive control board, or shock you into a startle reaction that causes a bigger injury. Oh, and simply turning a wall switch to off, that is never proof a circuit is safe. Honestly, if you remember nothing else from this explainer, make it this cardinal rule. Whenever humanly possible, work on a circuit only after it is de-energized, locked and tagged out, and tested for the absence of voltage. You verify your meter works on a known live source, you test the equipment to prove it's dead, and then you retest your meter. That is how the pros stay safe.
So, armed with the facts on AC power, magnetic induction, phase shifts, and strict safety rules, how are you going to apply this roadmap on your very first live service call? You've got the answers to the 50-question challenge now, but much more importantly, you have the underlying logic. When you walk up to a dead unit, you know how the AC flows, how transformers and capacitors shape it, and how to safely probe it with your meter. Keep this roadmap fresh in your mind, stay safe out there, and I will catch you on the next explainer.